Bismillahirrahmanirrahim. Assalamualaikum and a very good day to you all. In this video, I'm going to talk about the chapter 3.10, normal stress for beams in bending from Shickley Mechanical Engineering Design textbook. Okay, this is the chapter 3, load and stress analysis. Okay, so this is among the figures that in the textbook. Okay, you see the material is bending, meaning that the bar, okay, cylindrical bar or rectangular bar or square bar, you do the bending. Okay, you do the bending here, and like it's depicted in the figure 3.13 here, you see the arrow. You see the arrow here, meaning that it is a bending in the downward position. Okay, so there are B compression because it is the bending in downward position, and then there is a tension because the lower one will become the tension. This is the neutral axis. C is the centroid. Y is the C is the diameter of it. Okay, and Y is any point in the section that uh, uh, be from the center line until the outer layer of the bar. Okay, so bending and stress distribution. When beams bend, normal stress develop due to bending moment. These stress follow a linear distribution along the height of the beam. Key assumptions: pure bending, isotropic and homogeneous material obey Hooke law, and constant cross-section symmetry along the bending plate. Okay, we assume it is a pure bending, meaning that bending is not hampered by any things else lah. And then material are isotropic, meaning the same direction, and then it is a homogeneous material, meaning that it is the same material. It obeys the Hooke's law, F equals to Kx, and it has the constant cross section and symmetry along the bending plate, like depicted in this picture here. You assume that figure 3.13, it is has the constant cross section, the same material and the same geometry. Okay. For example, a steel beam loaded with bending moment experience maximum stress at extreme fiber and zero stress at the neutral axis. What this mean, the extreme maximum stress at extreme fiber? Here, see here, it is a maximum stress at this outer layer, the most outer layer of it. Okay, imagine it is a cylindrical rod. It is outer dimension. Yeah? Okay, as the extreme one. And then this neutral axis, the middle one is the neutral axis, meaning that theoretically nothing happened at the neutral axis lah. No compression and no tension. Okay, even though we bend it because everything goes into the bending. Okay, so zero stress at neutral axis. Okay, bending stress formula. The bending stress at the point distance y from neutral axis is given by stress equals to uh, m negative my per I, which is m is the bending moment, I is the moment of inertia. You can find the moment of inertia for the cylindrical rod is different from the for is the different formula. I for I beam is the different formula. I for the H beam is the different formula. I for the cylindrical rod is the different formula. You can find it in Google and everything. Okay, it has the linear stress distribution. Stress varies linearly with distance from neutral axis, from maximum compression to maximum tension in a reticular beam. For example, in reticular beam, the top experience maximum compression and the bottom experience maximum tension. This statement has to refer to this feature 3.13. Okay, because the bending is become downwards, so it has the top become the compression and the bottom one become the tension. Okay, so maximum stress at fiber extreme. Maximum stress always happen at the fiber extreme. Okay, imagine a rod, imagine a cylindrical rod, it is a outer layer. Okay, imagine a cylindrical bar, it is also an outer layer of it. Section modulus, simplified formula, stress maximum is over z, because where z is equals to moment of inertia over c. What is c? C refer to this picture 3.14. C is here. Okay, you see this picture here. Okay, and the simple calculation, this you do the calculation lah. Okay, and then principal application and conclusion. Bending stress equation is used in structural design to prevent failure. Engineers ensure that stress remains within the material's yield strength. Okay. Bridge construction example, design of steel girders in bridges considers maximum bending stress to prevent cracking or deformation under load. Conclusion, understanding stress distribution is essential for safe build design and structural integrity in engineering. So it is important for students in structural engineering to really understand this, because you want to build buildings. Okay, building needs to have some reinforcement, and you have to very have knowledgeable in this subject matter. Okay, that's all for the video right now. Inshallah, we meet in the next video. Thank you very much.